Far beyond the rugged coastline of Vancouver Island, where the cold waters of the northeastern Pacific conceal one of the most intricate networks of tectonic boundaries on Earth, instruments detected a sharp pulse racing through the crust. At approximately 208 kilometers, or about 129 miles, southwest of Port McNeill, British Columbia, a magnitude 5.6 earthquake struck at a shallow depth of approximately 10 kilometers, or about 6.2 miles, on the 20th of July, 2026. For many observers, one question surfaced almost immediately. Was this another sign that the Cascadia Subduction Zone was awakening, or had an entirely different tectonic system just reminded North America that multiple active plate boundaries share the same offshore waters? That distinction matters far more than it might seem. Western Canada and the Pacific Northwest are often viewed almost exclusively through the lens of Cascadia, the massive subduction zone capable of producing earthquakes approaching magnitude 9. Yet the offshore region west of Vancouver Island contains an extraordinary arrangement of moving plates, spreading ridges, transform faults, and fractured oceanic crust that routinely generate earthquakes entirely separate from the famous megathrust. Determining which structure produced a particular earthquake is not merely an academic exercise. It shapes hazard assessments, influences tsunami expectations, reveals how stress is distributed across the ocean floor, and improves understanding of one of the most geologically dynamic regions anywhere on the planet. At first glance, the location naturally invites speculation about Cascadia. Offshore Vancouver Island has become synonymous with discussions of locked faults, accumulated strain, and the possibility of another great earthquake similar to the event that struck in the year 1700. That catastrophic rupture extended for hundreds of miles along the continental margin, generating a tsunami that crossed the Pacific Ocean and reached Japan. Since then, countless scientific studies have focused on the gradual accumulation of strain where the Juan de Fuca plate descends beneath North America. Every earthquake occurring offshore tends to attract immediate attention because of its apparent proximity to that enormous fault. Location alone, however, does not tell the entire geological story. Precise coordinates place this earthquake near latitude 49.408 degrees north and longitude 129.342 degrees west, well offshore from Vancouver Island, in an area dominated by a different tectonic environment. Rather than lying directly above the locked interface where an oceanic plate dives beneath the continent, the epicenter falls within a complex offshore network associated with the Explorer Plate, the Pacific Plate, and the structures that separate them. Unlike the massive Pacific Plate or the larger Juan de Fuca Plate, the Explorer Plate occupies only a relatively small portion of the northeastern Pacific Ocean. Despite its modest size, its geological importance is enormous. It represents the fragmented remains of what was once part of the much larger Farallon Plate, an ancient oceanic plate that for tens of millions of years was consumed beneath western North America through continuous subduction. As the Farallon Plate gradually disappeared beneath the continent, only scattered remnants survived offshore. Among those remnants are the Juan de Fuca Plate, the Gorda Plate farther south, and the Explorer Plate near northern Vancouver Island. Although comparatively small, the Explorer Plate behaves as an independent tectonic block with its own pattern of deformation and movement. Instead of moving uniformly as one rigid slab, the plate experiences internal stresses generated by neighboring plates moving in different directions at different speeds. This creates an environment where fault systems remain exceptionally active despite the relatively limited size of the plate itself. Surrounding the Explorer Plate are several major tectonic boundaries that continuously reshape the ocean floor. To the west lies the immense Pacific Plate, moving generally toward the northwest. To the east, the Juan de Fuca Plate continues its long descent beneath the North American continent along the Cascadia Subduction Zone. Between these neighboring plates lie spreading centers that manufacture new oceanic crust and transform faults that accommodate sideways motion as the plates slide past one another. One of those transform boundaries has attracted particular attention following the recent earthquake. Known as the Sovanco Fracture Zone, this offshore fault system forms part of the boundary separating the Explorer Plate from the Pacific Plate. Rather than forcing one plate beneath another, the Sovanco Fracture Zone primarily accommodates horizontal movement. Massive blocks of oceanic crust grind sideways past each other, releasing accumulated stress through strike-slip faulting, similar in principle to California's San Andreas Fault, although formed in an entirely different marine setting. Transform faults exist because Earth's tectonic plates rarely move in perfectly parallel directions. Along mid-ocean ridges, where new crust forms, spreading segments are often offset from one another. Transform faults connect these offset ridge segments, allowing adjacent pieces of crust to slide laterally while accommodating differences in spreading direction. Over millions of years, these faults become long-lived structural features capable of generating repeated earthquakes as accumulated stress periodically exceeds the strength of fractured rock. Geophysical surveys have revealed that the Sovanco Fracture Zone stretches across the northeastern Pacific as an important structural boundary linking segments of the Explorer Ridge to surrounding plate systems. Although invisible beneath thousands of feet of seawater, the fracture zone represents a persistent zone of weakness extending through the oceanic lithosphere. Repeated earthquakes over decades demonstrate that stress continues to accumulate and release along this offshore boundary. Several characteristics of the recent magnitude 5.6 event strongly align with this tectonic setting. Perhaps the most significant clue comes from its depth. The earthquake originated approximately 10 kilometers, or roughly 6.2 miles, beneath the seafloor. Such shallow depths are entirely consistent with transform fault earthquakes occurring within oceanic crust. Oceanic lithosphere near spreading centers and transform boundaries is relatively thin compared with continental crust, allowing earthquakes to occur close to the surface as faults fracture brittle rock. By contrast, earthquakes associated directly with the Cascadia megathrust generally occupy a different geometric setting. The subduction interface slopes gently beneath the North American continent. Offshore near the trench, portions of that interface may indeed be relatively shallow, but earthquakes occurring on the locked megathrust are typically positioned farther east beneath the continental margin as the descending plate gradually dips beneath the overriding crust. An epicenter located this far offshore, combined with the shallow focal depth, fits much more naturally within the oceanic plate boundary system than along the principal Cascadia interface. Magnitude also provides an important piece of the puzzle. A magnitude 5.6 earthquake certainly represents a significant release of energy. People would readily notice shaking if located nearby, and instruments across Western North America would detect the seismic waves with ease. Nevertheless, this magnitude falls comfortably within the expected range for transform fault earthquakes occurring along active oceanic fracture zones. The Sovanco Fracture Zone has produced numerous moderate earthquakes throughout the modern instrumental record. Most events fall between magnitudes 4 and 6, reflecting the repeated release of stress along relatively short fault segments, rather than the simultaneous rupture of hundreds of miles of fault that characterizes great megathrust earthquakes. Earthquakes generated directly by the locked Cascadia interface occupy a very different statistical pattern. While smaller earthquakes can occur within the broader subduction environment, the central locked portion of the megathrust has remained remarkably quiet throughout historical observation. That seismic silence forms one of the defining characteristics of Cascadia. Instead of releasing strain through frequent moderate earthquakes, much of the fault appears to accumulate stress over centuries before releasing enormous amounts of energy during exceptionally large events. This contrast often surprises those unfamiliar with subduction zones. A region producing many moderate earthquakes is not necessarily the one storing the greatest amount of strain. In fact, the opposite may sometimes be true. Locked faults capable of producing giant earthquakes often exhibit prolonged periods of relative seismic calm because the opposing rock masses remain firmly stuck together instead of slipping gradually through repeated smaller ruptures. The offshore waters west of Vancouver Island therefore present a fascinating paradox. One tectonic boundary experiences regular moderate earthquakes as crustal blocks slide laterally past each other, Nearby, another far larger boundary may remain comparatively quiet while silently accumulating strain destined for a future rupture of vastly greater dimensions. Distinguishing between these systems requires careful examination of every available clue. Geographic position represents one line of evidence. Earthquake depth provides another. Regional tectonic architecture offers additional insight. Yet perhaps the most valuable information comes from understanding precisely how each tectonic boundary accommodates motion. Unlike subduction zones, where one plate descends beneath another through compressional forces, transform boundaries primarily accommodate horizontal displacement. Imagine placing both hands flat on a table and sliding one hand forward while pulling the other backward. Neither hand moves beneath the other, yet friction develops continuously along the line separating them. Eventually, resistance gives way through abrupt motion. That simplified demonstration captures the essential mechanics of strike-slip faulting. Within the Sovanco Fracture Zone, enormous slabs of oceanic crust behave similarly, although the scale is almost impossible to comprehend. Individual sections of lithosphere extend for hundreds of miles while reaching several miles in thickness. Their movement measures only fractions of an inch to a few inches each year. Yet over decades and centuries, those seemingly insignificant increments accumulate substantial elastic strain inside surrounding rock. When fault strength is finally exceeded, stored energy escapes almost instantaneously as seismic waves that travel through Earth's crust in every direction. Modern seismic networks record those waves using hundreds of highly sensitive instruments distributed across Western Canada, the United States, and the Pacific Ocean. By comparing the arrival times of different seismic wave types at multiple stations, researchers determine the earthquake's location, depth, and magnitude with remarkable precision. Even before detailed fault plane solutions become available, these fundamental measurements often reveal whether an event most likely originated within a transform fault, a spreading ridge, an intraplate fracture, or a subduction interface. For the earthquake southwest of Port McNeill, the available evidence points strongly toward the offshore transform boundary associated with the Explorer Plate and Pacific Plate rather than the famous megathrust farther east. Even so, another important tectonic feature remains part of the broader geological picture. Not far from the Sovanco Fracture Zone lies an active spreading center where entirely different forces continuously manufacture new sections of Earth's oceanic crust, adding another layer of complexity to one of North America's most remarkable plate boundary systems. Fresh crust is continuously created along that nearby spreading center known as the Explorer Ridge, an underwater mountain chain that forms part of the extensive ridge system stretching across the northeastern Pacific. Unlike transform faults, where plates slide horizontally past one another, spreading ridges mark places where tectonic plates gradually pull apart. As they separate, molten rock rises from Earth's upper mantle, cools rapidly upon contact with seawater, and solidifies into brand new oceanic crust. Although the annual rate of spreading measures only a few inches or several centimeters each year, the cumulative effect over millions of years reshapes entire ocean basins. Explorer Ridge therefore serves as the birthplace of the Explorer Plate itself. Every increment of newly formed basalt adds material to the plate before it begins its long journey away from the ridge. That movement eventually brings the crust into contact with neighboring plate boundaries, including the Sovanco Fracture Zone to the northwest and the Cascadia Subduction Zone farther east. Each boundary accommodates motion in a different way, creating an offshore environment where extension, sideways movement, and compression all occur within a relatively compact area. Earthquakes generated directly along Explorer Ridge possess their own recognizable characteristics. As tectonic plates move apart, tension develops within the brittle upper crust. Faults responding to that stretching commonly experience normal faulting, meaning one block of crust moves downward relative to the other as the surface extends. These earthquakes also tend to occur at shallow depths because the newly formed oceanic crust remains relatively thin and hot. At first glance, a magnitude 5.6 earthquake at a depth of approximately 10 kilometers, or about 6.2 miles, might appear compatible with activity along the ridge itself. That possibility cannot be dismissed solely from magnitude and depth. However, the reported epicenter lies somewhat southwest of Port McNeill, in an area that aligns more closely with the transformed structures connecting segments of the ridge rather than the ridge axis where seafloor spreading is concentrated. Geological maps compiled through decades of marine surveys show that the Sovanco Fracture Zone occupies precisely this transition between spreading segments. These fracture zones act as tectonic transfer systems, absorbing differences in movement between adjacent portions of the ridge while allowing the Pacific Plate and the Explorer Plate to continue their independent motions. Because transform faults remain active well beyond the spreading axis itself, they often generate earthquakes over much broader areas than the volcanic ridge crest alone. That geographical relationship explains why the Sovanco Fracture Zone currently stands as the leading candidate for the source of the earthquake. Based on the available hypocenter, depth, and regional tectonic framework, the probability strongly favors strike-slip motion occurring along this transform boundary instead of extension directly at the ridge. There remains another possibility, although considerably less likely. Oceanic plates are not perfectly rigid slabs. Internal deformation occasionally occurs within the Explorer Plate itself as inherited fractures reactivate or new faults develop under changing stress conditions. Such intraplate earthquakes can occur away from the principal plate boundaries, especially within regions where previous episodes of faulting weakened the crust. Because the Explorer Plate occupies such a mechanically complex setting between several larger plates, scattered intraplate seismicity has been documented throughout the instrumental era. Even so, the present event does not fit that explanation as neatly as it fits activity along the Sovanco Fracture Zone. The location corresponds closely with a well-established transform boundary already known for producing repeated moderate earthquakes. Invoking a less common intraplate source is therefore unnecessary unless future evidence points elsewhere. Attention naturally returns to the possibility that concerns residents throughout the Pacific Northwest more than any other. The Cascadia Subduction Zone stretches for approximately 700 miles, or nearly 1,100 kilometers, from Northern California through Oregon and Washington before continuing offshore Vancouver Island toward British Columbia. Along this immense convergent boundary, the Juan de Fuca Plate slowly descends beneath the North American Plate at an average rate approaching approximately 1½ to nearly 2 inches each year, or roughly 4 to 5 centimeters annually. That movement has persisted for millions of years. Unlike transform faults, where plates simply slide past one another, subduction zones involve one tectonic plate diving into Earth's mantle beneath another. Friction prevents smooth movement across much of the fault interface. As decades become centuries, elastic strain accumulates within both plates until resistance is finally overcome. When rupture eventually begins, hundreds of miles of fault can fail within minutes, releasing energy on a scale far beyond that of ordinary earthquakes. Evidence preserved in coastal marshes, offshore sediments, submerged forests, and tsunami deposits demonstrates that Cascadia has produced repeated great earthquakes throughout prehistoric time. The most recent occurred during the winter of the year 1700, generating violent coastal subsidence and a tsunami that crossed the Pacific Ocean before striking Japan. Geological records indicate similar events have recurred many times over the past several thousand years. Those facts understandably cause concern whenever offshore seismic activity occurs. Yet one earthquake should never be interpreted in isolation from its tectonic setting. Despite occurring west of Vancouver Island, the recent magnitude 5.6 event lacks several characteristics expected of rupture on the locked Cascadia interface. The epicenter lies considerably farther offshore within the oceanic plate system. The focal depth remains shallow and consistent with oceanic crust, rather than the principal plate interface beneath the continental margin. The magnitude also fits the long-established behavior of offshore transform faults, which routinely produce moderate earthquakes without involving the megathrust itself. Most importantly, the regional distribution of seismicity has historically distinguished these offshore transform systems from the relatively quiet locked portion of Cascadia. Moderate earthquakes occur regularly around the Explorer Plate, Explorer Ridge, and associated fracture zones because those structures accommodate continuous deformation through repeated fault movement. Cascadia, by comparison, releases accumulated strain much less frequently across its principal locked interface. That does not mean the systems are entirely unrelated. Every tectonic boundary within the northeastern Pacific forms part of a larger network transmitting stress across thousands of miles. Motion of the Pacific Plate influences the Explorer Plate. Explorer Plate deformation interacts with the Juan de Fuca Plate. The Juan de Fuca Plate ultimately converges with North America along Cascadia. Forces applied at one boundary inevitably influence neighboring structures over geological timescales. However, influence should not be confused with direct causation. No evidence currently indicates that this earthquake represents the beginning of a Cascadia megathrust rupture. Earthquakes occur every year throughout the offshore plate boundary system without progressing into giant subduction earthquakes. Distinguishing normal background seismicity from genuinely unusual behavior remains one of the most important responsibilities of modern seismology.